let's have a look on what happened in the most general problem, Newtonian viscous fluids. No perfect fluids, but now viscous. What does it mean? That, going back to the beginning of this chapter, that hypothesis that we did here is that these terms were negligible, so this lambda and mu were negligible, and no matter how big are the rate of strains, how large are the rate of the strains, the stresses have a hydrostatic stress state, which is true for perfect fluids. Now we just release this assumption. Okay? So now let's have a look to the problem, and the problem looks like that. What equations we have? We have the conservation of mass, the linear momentum balance, the energy balance, the mechanical constitutive equation, the entropy constitutive equation, the thermal constitutive equation, and the caloric and kinetic state equations. We have a grand total of 70 equations, partial differential equations, with 70 unknowns. Too large to be solved. Okay, so let's see what can we do with that. Let's consider first the motion equation, the equation of linear momentum balance, force equal mass times acceleration. It can be proven, and you will have it in the book, that whenever we see in these equations here, the divergence of d being the rate of a strain equation, the rate of a strain tensor, it can be expressed in this more convenient way. It's equal to 1/2 of the Laplacian of b. You know that the Laplacian is the divergence of the gradient, plus 1/2 of the gradient of the divergence of b. Okay, that is an identity. It's proven in the book. Okay, it's an identity. And second, this order identity that we have used a number of times along the course, whenever we have to take the divergence of a hydrostatic tensor, as is isotropic second order tensor, so and a scalar times the unity, that divergence is equal to the gradient of the scalar. Okay, these are two identities that we can use. So now let's look at the constitutive equation. The general constitutive equation for Newtonian fluids are this term, which is due to the pressure, to the thermodynamic pressure, and this term here that depends on the viscosities that now we are not neglecting. We don't neglect them. Well, what about trace of d? We have seen also sometimes the trace of d is equal to the divergence of it. That's another identity. So now, if we want to take the gradient, the divergence of sigma would be the divergence of the sum of the divergences of every one of these terms. So the divergence of all these is equal to the divergence of the first, but look, the divergence of these, the first one is a function, a scalar function times the unity, so we can apply that. So it's the gradient of p. That is the same. That is in a scalar multiplying 1, so is that case. Then lambda, which is a constant, comes out. So that is the gradient of the scalar part, of the trace of d. Okay? And that is just the mu times, look, and that one, whenever we take that, the divergence of d can be replaced by 1/2, which cancel with these two, that comes out, that leads to mu Laplacian of b plus mu gradient of divergence of b. So after replacing these equations into here, we see that this term in the fundamental equation or in the linear momentum equation can be written simplified in that way. So what we have done, look, what we have done is just replaced in that equation the constitutive equation. It's something similar to what we did in the Navier's equation in solids. You remember, to solve solid mechanics problems or elasticity problems in linear elastic problems in solid mechanics, what we call the displacement method, we replaced, we introduced, we substituted the stresses into the linear momentum equation. That's what we have done. So that we have substituted here, as we have done here, the stresses, that equation, into here, so we come up with that equation here, okay? These are the famous Navier-Stokes equations. Have you ever been told about the Navier-Stokes equations? Is that familiar to you? Well, I mean, that is a very, very important family of partial differential equations. Mathematicians consider this one of the most challenging partial differential equation systems to be solved in the more general case. Okay. So look, the concept I would like to bring here is that these are nothing else than the linear momentum conservation equation. Look, force, this is the body forces, equal mass times acceleration. And what is that? Well, that is divergence of sigma. So the local counterpart of the traction forces on the boundary. Okay? So this is still the linear momentum conservation equation, but written in terms of the velocity. The stresses doesn't appear here. Look that the velocity appears here, and the pressure, velocity and pressure. Nabla, the replacement of the velocity, body forces, time derivative of the velocities. This is a system of second order. Look, there are second order derivatives. Second order partial differential equations on space and first order differential equations on time. Three equations with four unknowns. There are three unknowns in the velocity, but don't forget that pressure is always here. So we have four unknowns and three equations, okay? But of course, when we try to solve that equation, the system is much more simplified in that way. Let's look now to the energy equation. The energy equation is another equation that appeared in the problem. No, that is the equation here, okay? The energy, now we have treated with that. Now let's treat with that. And then the energy equation says that the variation per unit of time of the energy, internal energy, is due to the stress power plus this term, which is nothing else than the heat power, heat creation into the body, okay? Look, let's consider this term here, okay? We also have seen that in the previous chapter that the stresses times the rate of strain can be written for a Newtonian fluid in that way. One part that we call the recoverable power, which is minus the pressure times the trace of D, and one part which depends on the viscosities, where we have here the bulk viscosity and here the kinematic viscosity, okay? That is what we call the recoverable power and the ECDF power. And then the Fourier's law that looks like that, Q is equal minus K gradient of theta, then whenever we have here divergence of Q, then we have to compute the divergence of K gradient of theta. Okay, so by replacing these two equations on that, we can rephrase the energy balance equation in terms of that. Rho du dt is equal to this term, which incorporates this term minus P trace of D, plus this term, K trace of squared D, plus 2 mu d prime d prime. Recall that d, remember that d prime is the, what is d prime? You know, remember what is d prime? Is the deviatoric part. Prime means the deviatoric part of the rate of a strain tensor. So, well, finally we have this equation here, and that is what is called the energy equation. Look that the energy equation now is written just in terms of the velocity, of the pressure, and the temperature. There are three variables involved here, and the internal energy, sorry, four variables, okay? So that is the equation of the energy equation, but now written in terms of the velocity and the temperature and the internal energy. That is the energy equation. So now, after this manipulation, we see that the problem gets simpler. We have the conservation of mass, the momentum balance, which is, don't forget, the Navier-Stokes equations are the momentum balance. Okay? Force equal mass times acceleration. Force and force equal mass times acceleration. The energy balance, the entropy constitutive equation, the caloric state equation, the kinetic state equation. What we have removed from here, the stresses. The stresses don't appear here. So now that means that instead of 11, we have now 8 scalar equations, 8 partial differential equations with unknowns, which are the density, the velocity, the pressure, the internal energy, the temperature, and the entropy. Okay? So I think that it's good to have an interpretation of these Navier-Stokes equations. Okay? So let's focus our attention on this equation here, the Navier-Stokes equation, right? That's the equation here. I said many times, this is force equal mass to acceleration. Okay, so let's understand a little more physically what is every one of the terms here. Okay? You know that force equal mass times acceleration, thus we can pass this term, which is acceleration, to the other time, and then they are called inertial forces, so saying that the force including the inertial forces is equal to 0. So any dynamic system is in equilibrium under the inertial forces, considering the inertial forces as minus the mass times acceleration, then this sum of forces are equal to 0. Okay? So now let's consider one component of this equation. So imagine that we are considering a particle of fluid like that, a particle of fluid, and we are considering one direction, one Cartesian, one axis of the system of coordinates. What do we have at every point? Look, minus gradient of p. What is the component in the direction I of minus gradient of p? Is the derivative of p with respect to xi. Look, the pressure. So in that side, the surface is subjected to the pressure. And in that side, the surface is subjected to the pressure too. If the length of this element, differential element, is differential of xi in that direction, we can say that the pressure at this side, is equal to the pressure at this side plus developing in Taylor series of up to the first order derivative of the pressure with respect to xi times differential of xi. So here we have a pressure P, and here we have a pressure in the opposite sense, which is P plus the derivative of P with respect to xi plus dxi. So the sum of both is just this part here. This part is the sum of both. So this is a force in that direction, look, that direction, which is the derivative of P with respect to xi per unit of size. If dxi is now the unit of divide that force by dxi, per unit of volume, the forces acting on this particle due to the difference of pressure at both sides is the derivative of p xi. So the component I of gradient of p. So this force here, including the sign minus, is nothing else than the forces due to the gradient of pressures, the balance due to the gradient of pressures at one side and the other side of the particle. That is one. Let's look at that, for instance. Well, that would be a force whose component in the direction xi will be bi. Okay, so rho bi is a force in the positive sense, which is that. So we have that force, which is gradient of p, but in the negative sense, and that force, which is rho v in the positive sense. This is the volume forces, the gravitational forces in our case. Okay? Look, what is that? Now it's important here. I've placed, look, there is a subtle, I've placed, instead of this plus here, I've placed a minus times minus. Okay, why? Because in general, if we compute in a flow this value here, this sign, the sign of this is negative. So that is if you place a minus sign in front, that is a positive sign. So this term with the minus is positive in general. So minus this term is a force in the negative sense. What is this force? Look, this force is proportional to viscosity. What is viscosity? It's like friction. Viscosity on this particle is the resulting, or is the force that is done by contact with the neighboring particles, by contact. Okay? So that viscous forces which act on the lateral surface of the element, which are minus lambda plus mu, they are times this term, they are proportional to the viscosities. They are viscous forces that increase as the velocity increases. So the larger are the velocities, or more important, the larger are the gradient of the velocities, the larger are the viscous forces. Okay? So if the velocities are constants, if there are not gradient velocities, these terms are 0 and these terms are 0, then there is no viscous forces. That is what happens when we have perfect fluids or when we have fluids at rest. In fluids at rest, there is no gradient of the velocities, so in consequence, all the terms of these viscous forces are 0. In perfect fluids, although the gradient of the velocities are not 0, the viscosities are so small that we consider that these terms are 0. But in Newtonian fluids, neither in the general case, neither the viscosities nor the gradients of the velocity are 0, and we have to consider these viscous forces characterized in that way, that they are opposing to the motion of the particle. So the particle that tends to move in that direction, then it's restrained by the action of the friction with the other particles, which turns out into this viscous force. So that term here is nothing else than the friction forces made by the neighboring particles due to viscosity. Now we have an interpretation of that. And then this term here is the inertial force. So the component in the direction in the xy, in the coordinate xy, is a negative, so in the direction negative, which is rho dv with respect to t. So this picture helps us to understand what is happening to a particle of a Newtonian fluid in the motion. So it has to be in equilibrium, so to speak, in equilibrium including the inertial forces, with the inertial forces, which are negative, okay? The gradient of pressure forces, which are negative too, okay? The gradient of pressure is a negative forces, opposite to the motion. And then, in favor of the motion, that is, there are the external forces, like that. And in opposite to the motion are the viscous forces. So there is a driving force, which is the body forces, okay, which is opposited by all these forces, the pressure gradient forces, which that work in opposition to them, the viscous forces, which are in opposition to them, and the inertial forces. Okay? And now let's do the same exercise in terms of the energy equation. Let's try to interpret the energy equation that looks like that, okay? What is that? Well, that is the variation of the internal energy. So look that the internal energy is all the energy minus the kinetic energy, right? That is what we saw in the corresponding chapter. So it says that the variation of internal energy, the rate per unit of time, of the internal energy per unit of volume, because this density here, variation of internal energy of the rate of internal energy per unit of volume, is due to all that. Let's try to understand that. Look, let's see some of the equations we have derived. Maybe you remember that we obtained that equation. The variation with respect to time of the differential of the volume is equal to the divergence of velocity times the volume. Okay? So, what is P? Okay, P can be understood in a particle as the pressure, the thermodynamic pressure, acting on this particle here. Okay? Look, what is P times gradient of B? Gradient of B can be understood as the variation of volume per unit of volume. Okay? So this term P times delta B means what is the work, the work done by the pressure per unit of time and per unit of volume, which is the P times the variation of volume times unit of volume. In other words, it looks like the work of all, the sum of the work of all these forces, of these pressures, per unit of volume. Okay? Which is negative, because these are compressive forces, so they tend to compress the forces and produce a negative work. What is this term here? Well, this term here you can identify. This is the internal sources term, and this is the heat conduction term. In other words, this is the heat generated by the internal sources and the conduction, the heat conduction at the point. And what is that? What is that? That is the forces, the viscosity forces. That is the work of what forces? That is the work of these viscosity forces. Okay? These viscosity forces also make work, and this is what is called the dissipative power. Okay? So in other words, we can say that in a fluid, in a Newtonian fluid, the internal energy variation is due to something. Well, a negative part, which is the compressive work, the work that is done for compressing the fluid. Okay? The work that is done for compressing the fluid. By the way, that work, if we compress the fluid, that work is negative. If the fluid is incompressible, then this term, the fluid cannot be compressed, and then this work is negative, is zero, sorry. You remember that the negative fluid, the divergence of the velocity is zero. Okay? Second, the internal energy also is made of that source, that heat that enters into the body per unit of time, either due to the sources, the sources, the chemical reaction or whatever, or due to the part of heat that the particle receives by heat conduction from other particles. That is the term here. And what is that? That is the work that is done by the viscous forces, the viscosity forces. So if the viscosity is zero in a perfect fluid, lambda and mu are zero, so are zero this k and mu, so this term disappears. Okay? And that viscosity is dissipative. That work is dissipative, so it's not recovered. It's not recovered. That is responsible because of irreversibility of the fluid motion. That work is dissipative, recoverable, and that work is dissipative. Okay?